Okay, good morning. Good morning to everyone. Good morning sa mga nasa Zoom. Hi Jason. Good night na, good evening yata dyan, no? And also good morning to those people watching live on YouTube. Okay, so today we are very lucky to have our speaker for this webinar. This is the One UP Applied Mathematics webinar. And our speaker today is uh, very special. He just finished his PhD studies from National Sun Yat-sen University in Taiwan. And he just came back in the Philippines after having going through many processes because of, of the community quarantine here in the Philippines. So now he's here in Bay Laguna. He is a faculty member of the Institute of Mathematical Sciences and Physics, University of the Philippines, Las Palmas. So without further introduction, let's welcome Dr. Eduardo Jatulan. Go, Edu.
Hello, can you hear me?
Yes, Edu. Go.
Okay, yeah. So before I start, so I just want to thanks Dr. Rabante for inviting me to deliver some talk about my results. So for today's talk, I will share some basic results that we had for quantum graphs, specifically associated with Archimedean tiling. So for today's talk, so we have the following outlines that we are going to follow. So I'm gonna consider some preliminaries, some introductions for basic definitions for quantum graphs, and then after that, so we're going to consider some dispersion relations. So we're going to define later what we mean by dispersion relations, and then after which we are going to use this dispersion relations to analyze the spectrum of these quantum graphs together with the occurrence of the Dirac points in its dispersion relations. Then we have some summary and conclusions. So first, we define what is Archimedean tiling. So Archimedean tiling, or also known as uniform tiling. So basically, it's just a tessellation of plane with regular polygons and only one vertex configuration. So what does it mean? So it means that in a plane, so to tessellate using regular polygons in one vertex, so we have here, for example, in one vertex, we only have a uniform polygons around it. For example, in this case, we have the octagon, two octagons, and one square. And then we can cover the whole plane just using these configurations. So for each vertex, we only have these configurations. Another example, so we have the hexagonal tiling. So at every vertex, we have three hexagons around this vertex. And throughout this plane, so every vertex, as we can see here, we only have hexagons around the vertex. That's why we call it the uniform tiling. Okay. And it is also known that the Archimedean tiling, we only have 11 Archimedean tiling that we can do. So we have here the triangular tiling. So it means we have six triangles. So we have this configuration, three. It means that we have the three sides of a polygon. Then six, we have six triangles around a vertex. Then we have a snub trihexagonal tiling. So it means we have four triangles and one hexagon, and so on up to, we have the most complicated here is the truncated trihexagonal tiling. So we have, all in all, we have 11 Archimedean tilings. So now let's define quantum graph. So basically, a quantum graph is a triple. So it involves a metric graph. We have the differential operator and some vertex condition. So basically, when we say a quantum graph, it is just our goal is to have some spectral problem of a one-dimensional one-dimensional Schrodinger operator acting on the metric graph, satisfying some vertex and boundary conditions. So a so we have a graph. So we have a basically, so if we have a combinatorial graph, so from a graph theory perspective, and then we say that it's a metric graph actually if each of its edge is identified as an interval in real number. So in metric graph, we are not only concerned with the vertices, so the edges are also involved in the graph. And later, so the metric graph that we are going to consider are these Archimedean tilings. Okay, so in this case, in this talk, we are going to consider a self-adjoint differential operator that acts in this mesh on graph. So these are just the collections of functions that are defined on each individual edges. So these are just the direct sum of this the L2 functions on each edges. And this differential operator acts as this one. So at its edge, so we have this one-dimensional differential operator, where our potential, we call this as the electric potential in this case, in L201. So locally, it's L2. And we have the domain of this operator. So, we have this, I think we have a typo. This one should be a gamma, L2 gamma. So we have this all functions in our graph, wherein it's L2. And locally, this function is in this Sobolev space. And we have this norm. The summation is finite. And we have these two conditions. So at every vertex, so we have here, the function value is equal at a given vertex. And the influx, so we have here the derivatives at the given vertex is equal to 0. So here we have this notation here that this is the set of all edges incident to V. Okay, so we have here the given functions defined on these edges, and at the given common vertex, the function value is equal to 0. And we call these two conditions. The first one, we call it as the continuity, and this one is the Kirchhoff conditions. And together, we will call them Neumann conditions. So later, I will give some examples, and then we will see why we call these Neumann conditions for quantum graphs. So I'll give you a trivial example of this quantum graph is an interval 0, an interval from 0 to A. So we have length for this interval A. So this is a trivial example of quantum graph. So the Schrodinger operator that we are going to consider is this differential operator here acting on this interval. And of course, the continuity condition at every vertex is empty, since we only have one edge for this quantum graph. And the Kirchhoff condition at vertex 0. So we have the line at vertex 0. We have this f prime of 0 is equal to 0. And at the vertex A, it becomes negative f prime of A is equal to 0. Okay, and it is well known that if we set for us, if we set our Q to be equal to 0, then the eigenvalues of this operator acting on this segment will be these eigenvalues. We have the n pi over A squared, where n goes from 1 to infinity. And this corresponds to some eigenfunctions. F of x is equal to cosine pi nx over A. So as we can see here, from the Kirchhoff conditions, so this boundary conditions, this will give us the Neumann conditions for our problem on the line segment. Another non-trivial example of a quantum graph is the star graph. So we have this graph with the common vertex at this given vertex, and then the length of each edge. So we have here the lengths are not the same. So we have A1, A2, and A3. So at these boundaries, following the Kirchhoff conditions, we have here the it will satisfy the Neumann conditions for these endpoints. And now we have here at each edge, we will satisfy these differential operators. So again, our goal is to get the eigenvalue for this quantum graph associated with this star graph. So in that case, we have the following eigenvalue equations. So we have here y double prime is equal to again the assumption here is that our Q or the potential is equal to 0. So we have the following three equations at each edges. So at each edge, and then we have here the Neumann conditions. So this is the Kirchhoff condition at the center vertex. And wait, so as we can see here, we have the arrow indicating that we will parameterize this locally, this quantum graph, as we have the local coordinates we have coming 0 to A3, 0 to A2, 0 to A1. So these are the endpoints. And the common vertex, we have the continuity conditions. So from the continuity conditions, the function value here are the same. And then we have the Kirchhoff conditions. So we have the derivative, the sum at this derivative at this point locally. We have A1, A2, A3 are, so the sum is equal to 0. So from these conditions, we can actually derive the eigenvalue for this star graph. So if we set our lambda to be the rho square, then the first two conditions can be solved by the following functions. So wherein our A1, A2, A3 are some constants. So we have Y1 will satisfy this given first equation together with the initial condition. And thus we have here to, so we have this function solving these first two equations. And then using 3 and 4 conditions, we come up with these equations. We have A1 cosine of rho A1 is equal to A2 cosine rho A2 is equal to A3 cosine rho A3, and together with this one. And now the if we divide both sides, since they are equal, we can divide by cosine A1 here. We divide this A2 cosine, and then so on. Then we'll come up with this given equation. Tangent rho of A1 plus tangent rho of A2 plus tangent rho of A3 is equal to 0. So now the idea is to get the eigenvalue, just like what we have in matrices. So we want to get the value for this for a non-zero solution. So in this case, the eigenvalues are the square root of this rho, okay, that will satisfy these given equations. So those values of square root of rho satisfying this will be our eigenvalues, okay? And another thing is that aside from this way of solving, the method that we are going to use for the succeeding slides will be the so-called characteristic functions. And for the characteristic function is that for us to get a non-zero functions here, to get a non-zero function, it is equivalent to saying that this given equation, so we have here a system of equations, we're going to have a non-zero values for A1, A2, and A3. In that case, it means that to have a non-zero values or solution for this A1, A2, and A3, that is equivalent to saying that this matrix, so we have here, is equal to 0. The determinant of this matrix is equal to 0. These are just the coefficients of these equations. Okay. So now, so the idea is to get the eigenvalue. So all we have to do is to simply consider this characteristic function. So I think this should be rho. And all we have to do is to equate this and to come up with this equation. So this is actually equivalent to what we have derived a while ago. So this is more robust, but this is longer equations. But this also solves, from here, we can also get our eigenvalue. Of course, here in the previous one, we can explicitly solve for our lambda in the case that our length are all the same. Okay, so now we have the idea for characteristic functions, but the quantum graphs that we are going to consider here is not actually finite. So we're going to have an infinite quantum graph. It means that the graph, the edges are infinite. So the number of edges is infinite. So and specifically, we are going to consider as periodic quantum graph. So a periodic quantum graph, I'm going to define periodic quantum graph that is embedded in the plane, since the quantum graph that we are going to consider are the Archimedean tilings. So we have a more general definitions for periodic quantum graph, but in this talk, I'll just give you the definition that is you have the quantum graph that can be embedded in R2. So given this point P1, P2 in Z2, and then we have a fixed basis for in R2, and we have this notation P circle S to be action of Z2 on a given S subset of our graph. Okay, and it's defined by this translation shift or shift operator. So we have here P dot K is just P1, the dot product of P and K here. And an infinite quantum graph is said to be periodic if we have the following. So we have here G is, I think I mixed up with G and gamma. So G here is invariant under shift by this one. So it means that if we have a point in the in our graph G, then if we translate it using the shift, then it's still on the graph G. And another one, there exists a compact set W subset of our graph, such that if we translate this compact via this shift, it's if we translate it, it will cover the whole graph. So from here, so we have a compact subset, and for any P and P prime in our Z2, then the intersection of this shift is finite. Okay, and we call this W as fundamental domain in this case. Okay. So as I've said, we have a general definition for periodic quantum graph. So we can refer to this book. This is a comprehensive introduction for quantum graph. And a function Q is said to be periodic if we have this Q of X plus this translation is just equal to Q of X for all P in Z2 and X in our graph. So now let's have this Floquet block theory. So this we're going to use this to analyze our spectrum. So if we have given this operator to be our operator acting on the periodic metric graph G with W as fundamental domain, then as we can see here, if we have this transformation U acting on LG2, so we have L2 of G, then we have this transform given in this given function. Okay, so from Floquet block theory, it means that our operator is unitarily equivalent to this direct integral. So direct integral is just a continuous counterpart of the direct sum, wherein this operator H theta is just the restriction of our operator on W, with some additional conditions. We call it the block conditions, wherein we have this y of x plus the shift is just equal to this phase factor times y of x for all x in our fundamental domain, and P1, P2 in Z2. So following some terms from physics, we call this theta here as our quasi-momenta, and B as the Brillouin zone. So this B here, we call this as our Brillouin zone. It's from negative pi to pi squared. So this one is a square with side negative pi to pi. So from this Floquet block theory, we can actually have some result that if we want to study the spectrum of our operator acting on our metric graph, we can just consider this our restriction to our fundamental domain. So we can just consider a compact subgraph of this quantum graph. And it is known that the spectrum of our Hamiltonian or our operator is can be decomposed into three. So we have the absolutely continuous spectrum, we have the pure point spectrum, and the singular continuous spectrum. And since we have a self-adjoint operator, the singular continuous spectrum will be empty. So we're going to have our spectrum will be composed of absolutely continuous and pure point continuous. As opposed to elliptic operators, we know that the spectrum are just absolutely continuous. We don't have pure point. But in quantum graph, we can have a pure point spectrum. This is due to the unique continuation property may not hold for quantum graphs. Okay, so this unique continuation property is popular in the elliptic operator theory. So now, in that case, we can have the pure point spectrum for this operator H are actually have infinite multiplicity, and it is determined by the presence of L2 eigenfunctions, or we're going to have some compactly supported eigenfunctions corresponding to this pure point spectrum. And for our absolutely continuous spectrum, we expect it to be some band and gap structure. So now let's define what is this dispersion relation. Dispersion relation is just of H is defined as the multi-valued function that maps each, we have here theta from the quasi-momentum, from the Brillouin zone to the spectrum of this H theta. So the spectrum of each this H theta for a given specific value of theta, the spectrum of this is discrete, since this is a compact, this acts on a compact graph. Okay, but collecting all those multi-valued functions, and then we can come up with this. For example, in this figure, so we have this our Brillouin zone. So dispersion relation is just the multi-valued functions. So for example, at a given specific value of Brillouin zone, let's say for example theta 1, theta 2, then we can have the discrete eigenvalues for H theta. Then collecting all those, we can come up with this beautiful structure, and we call this as the graph as the block variety. And here, so we have here the function lambda j theta. In this case, we call this as the J band function, or the dispersion relation branch. And then the range of this J band is called the spectral band. So we have here the spectral bands. And then another J+1 spectral band is somewhere here. Okay. And another interesting phenomenon for this dispersion relation is the occurrence of this Dirac point. So Dirac point in the dispersion relations are basically the points where different sheets touch to form a conical singularity. So this we have here a given point. Then around this we can form a conical. So we have two cones touching at a given point at a single point. So this kind of phenomenon is very interesting for the physics side. The Because in this case, if we have this the dispersion relations for the energy with respect to our quasi momentums are linear. So in that case, the consequence are that the particle moving around this will have a high mobility around this given, and this implies lots of good properties, for example, for some materials in the nano. Yeah. So we have here, and now as we can see, as I've mentioned, that we have here the quantum graph. So basically, we're going to use operator on R. So just recall some of this. So if we have a one-dimensional Schrodinger operator, okay, where Q has a period A, then we define these functions. We have the cosine-like functions and the sine-like functions. With these initial conditions, we have a C at 0, S prime at 0 is 1, C prime 0, S at 0 is equal to 0. And with this rho is equal to square root of lambda. And if we define the Hill discriminant, delta of lambda, as this C of A plus S prime of A. And so these functions evaluated at A, we will denote A as just C and S prime. So we have C plus S prime. So we're gonna need these notations later. And another thing that I want to emphasize is that if our Q is even, so if our Q is even, then this C and S prime are equal. So delta will be just 2S prime. So this S prime and delta are related if our Q is even. So here by Floquet block theory, we can actually get the spectrum of this Schrodinger operator. That this is this rho squared is in the spectrum if and only if this equation is satisfied. So these are all the lambda that satisfy these equations for some theta in this interval. So for the given, if we consider the line, this is the so-called the dispersion relation, and we have here its Brillouin zone for the line. And it's also equivalent to saying that this is a spectrum if all the lambda will satisfy this given inequality. Okay. So now we're going to have some the quantum graphs associated with Archimedean tilings. So what are the motivations why we study these quantum graphs? So the first is that the Luo in his thesis attempted to study this. But he only derived some 2 of them out of 11 with the square tiling. So we have this square tiling, and we can consider this a fundamental domain for this square tiling. Okay, and he come up with this result, the dispersion relation for square tiling, considering that we have a different in this fundamental domain. If we consider different potentials along this, so we have Q1 potential, Q2, Q3, Q4, and then we'll come up with this dispersion relation. But if we assume that our potential here are all the same and even, we can simplify this further. So even along this edge, then we come up with this simplified version of our dispersion relations. And from this dispersion relation, we can analyze more about the spectrum of this given quantum graph. So again, this S is the S function satisfying the one-dimensional operators. This A means S of A, and then we have S prime of A. And another one, he also considered the truncated square tiling. So we have a configuration at vertex, one square and two octagons. So he derived this dispersion relations. If we have a Q along the edges in the fundamental domain, they are the same and even, then he come up with this dispersion relations. But he considered this fundamental domain. But our goal here is in this talk we consider as much as possible the simplest fundamental domain. So in that case, we consider this given. Okay. So what motivates us to study this quantum graph is that this quantum graph will serve as simple model for graphene and its related allotropes. Of course, the assumption here for us to approximate the band and gap structure of graphene and its related allotropes is that we have the particle is spinless and it moves along this metric graph. So we have this structure. So this is the structure of a graphene and other related allotropes. And as we can see here in the Archimedean tiling, this number 11, we have this is the truncated hexagonal tiling. And then another one, number 7, this is the truncated square tiling. We have here number 8 also. And yes, so we have here 1, 2, 3, 4, 5. Among these structures are in our quantum graph associated with Archimedean tiling. So another thing is that aside from the square tiling, truncated square tiling, the most studied one is the hexagonal tiling, since this is a structure of a graphene. So graphene is an atomic scale hexagonal lattice made up of carbon atoms. So this is a monolayer of a graphite. So we have the Cookman and Post in 2007 actually derived the dispersion relation for hexagonal tiling, wherein QIs are the potential in the fundamental domains are identical and even, and then they derive this dispersion relations. And I want to emphasize this one. So by this chemist Amovili, Leys, and March in 2004, by the quantum network model, they estimate the potential function along the edges of this hexagonal tiling to be equal to this function. This QFX is equal to negative 0.85 plus d over 1.34 sine squared of this pi x over d. So this d here is the distance between neighboring carbon atoms, and we have this d very small quantity. And for the Dirac points, Cookman and Post also showed that there exists infinitely many Dirac points at this given point. So we have the lambda star and then plus or minus theta star, wherein this lambda star satisfied this given equation. So these are all the lambda wherein our S prime A is equal to 0, and theta star is located at this given point, 2 pi over 3 and negative 2 pi over 3. This is a point in our Brillouin zone for any even potential Q. And Pfefferman and Weinsteins, and also Bercolayco and Comek. So they consider, but in this case, they consider this operator acting along the this is not their model is not a quantum graph, but their operator also acts inside the hexagon. And then they also showed that there exists infinitely many Dirac points for any epsilon here, except for a countable set. So these points occur at a double generacy at a specific quansi momenta. So the Dirac points occur at this given point also. Also for the graphene, so this is some example of the allotropes of graphene. So Du and Cookman also derive the dispersion relations for graphene. So we have these equations. Yeah, this is actually the simplest allotropes that I've showed a while ago. They consider this, and they also showed some Dirac points for this given structure. Now let's have our start with our triangular tiling, and so in this assumption is that we have here we have here a triangular tiling, and as we can see, we will consider this fundamental domain. And this fundamental domain, if we translate, it will cover the whole graph. Okay, so the assumption here is that we have here the potentials along this potential. We have Q1, Q2, and Q3. And of course, if we translate, this potential is the same with this potential here. So now if we consider this fundamental domain, so we can cut this through the edges of this quantum graph. And then we have here, we can say this is Q5. We have the potential 5, Q5, and then we have this potential Q2. And as our assumption here before, we have the potential here is the same with this potential. So the potential Q5 is equal to potential of Q2. Same with this one, we have the potential Q6. Same with potential Q3, potential Q4, potential Q1. And we have here the y's, yj's. They are the functions satisfying this given at the edge, they define at each edge of this quantum graph. Okay, so we have this, and from as we can see that we have this at vertex 1. We have the continuity conditions, and we have this Kirchhoff conditions. Okay, so we have here, this is the vertex 1. So again, locally we have here, we parameterize. It means that locally we have 0 to A. And again, our assumption here for our triangular tiling, all the edges are the same with length A. Okay, so we have here all the edges are the same. The length of the edges is the same with length A. So we have here the Kirchhoff and continuity conditions, and also with the vertex 2, 3, and 4. And now since Q1 is equal to Q4, Q2 is equal to Q5, Q3 is equal to Q6, then by uniqueness of solutions, we can actually have these relationships. Y1 is just equal to this Y4 with some phase factors. Okay. So from that, we can actually have these equations. So we have these notations for EI theta 1 and EI theta 2. And we have these YJs. So as I've said, these are the solutions. So it means it satisfies the linear combination of CJ and SJ with this constant AJ and BJ. So we have this given equations. We derive this from the Kirchhoff and continuity conditions. And also this we have here, we get these values from our from our block conditions. And again, our goal is to get we can have a non-zero values for A2, B1 to A3, B1 to B3. Okay, satisfying these given equations. And that in that case, we'll just consider the characteristic function, and this characteristic function must be we will to get the spectrum is to get the value of rho that will make this characteristic function 0. And then first, let's simplify this. So I will not. So all you have to do is to simply get the determinant of this one. So again, this triangular is the simplest one. So we only have 6 by 6. The most complicated one will gonna have a 36 by 36 matrix. So I think I'll just move to this one. So for the periodic quantum graph associated with triangular tiling, the characteristic function is given by this one. So again, this CSS here is just denoted as C1, S2, S3, C2, S1, S3, C3, S1, and S2. So this one. So uh, and it's clear here that all the lambdas, wherein lambda is equal to rho squared, is the spectrum of the problem if and only if this one is equal to 0. Okay, so this is our result here is the equation is complicated since we did not assume our Q to be even along the edge and unique. So now if we assume that our potential is even, then we can come up with this Lagrange identity that the CS prime minus C prime S is equal to 1. And of of course, this quantity, even Q is not even, is also this also holds. And when Q is even, then we know that C and S prime are equal. Then if we assume all Qj's are identical to Q and even, and we let this quantity to be cosine theta 1, cosine theta 2, cosine theta 1 minus cosine theta 2, then the dispersion relations for this triangular tiling will be this given expressions. So again, this is the simplest expressions that we got from this Archimedean tiling. And so the rest, I will not show how we solve this one, but I'll give you the fundamental domain that we consider for elongated triangular tiling. We have this. Actually, the most complicated is the truncated trihexagonal tiling. The matrix that we got here is around 36 by 36. So I'm not that good in manually solve this manually compute this matrix. So I use the Mathematica to solve this. But after using Mathematica to compute for the determinant, the expressions the expressions are still complicated. So we need to be patient. And the following are the dispersion relations that we derived. So we just noticed that mostly all of them, if the fundamental domain is a parallelogram, all of them has this given expressions, this eta. Okay. So we have, and then this one, as we can see, we have complicate. But the thing here is that they are functions of S prime. So they are polynomial of S prime, our dispersion relations. And we have some factors here that doesn't depend on our Brillouin zone, our quantum moment, quasi-momenta. So another thing, so we have here, this is the most complicated dispersion relation that we solve. So again, these are all polynomials in S prime. So from here, from the dispersion relations, we can analyze more about the spectrum of our quantum graphs. So again, all the value of lambda that does not satisfy does not depend on our quasi-momento will be the pure point spectrum, and the other one, if it depends on our theta 1, theta 2, will be composed of our absolutely continuous spectrum. Okay, so we have the following for the pure point spectrum. We have the triangular, elongated, truncated, snub, square tiling, rhombi, trihexagonal tiling, snub, trihexagonal tiling, truncated, hexagonal tiling. They all coincide and given by this set. And actually, for this one, this is just the eigenvalue of a Schrodinger operator acting on the line with acting on a line segment with boundary conditions Dirichlet. Okay. So and then the rest, we have the trihexagonal tiling and truncated hexagonal tiling. So these are the configurations. So it means that we have a triangle, hexagon, triangle, hexagon. So we have this one, the Dirichlet, together with this S prime of A is equal to -1/2. And for truncated hexagonal tiling, we have additional condition here. So we have, aside from S of A is equal to 0, we have S prime of A is equal to 0, S prime of A is equal to 0. So all these are all the pure point spectrum for the quantum graphs. And as I've mentioned a while ago, that this corresponds to uh, eigenfunctions with infinite multiplicities. So for the case that our pure point spectrum is S of A is equal to 0. So it means that, for example, if we have the quantum graph with the hexagon, we'll just move around and consider some at each edge. We have here, we have the edge, and at each endpoint, we consider the Dirichlet conditions. Dirichlet means that the function value at these endpoints, the function values are 0. So and then we move along this edge, so we can come up a function satisfying this Dirichlet, and the rest of the graphs, the functions will be 0. So in that case, we have the eigenfunctions, and we have infinite many hexagons, so we can choose any hexagons we have. So it means that we have an infinite eigenfunctions corresponding to this given pure point spectrum. I think same idea about this, but I think I'm gonna skip this one. So these are just the eigenfunctions corresponding to the pure point spectrum. And for the absolutely continuous spectrum for even potential, so we have the dispersion relations. For example, I think we for this triangular, we skip this for square tiling. For triangular, the dispersion relations is this one. So we know that this rho squared is in the absolutely continuous spectrum if and only if we satisfy this given equation. And since we have this range is -1,8 to 1, then we conclude that this is in its spectrum of triangular tiling if and only if we have this S prime of A is in this given interval. So from here, we characterize all the absolutely continuous spectrum. And this is well-known expressions in our one-dimensional Schrodinger operator. And we have lots of results from well-known results for the one-dimensional Schrodinger operator. And we can use that to further analyze this given characterization for our absolutely continuous spectrum. And to summarize all, of course, these are just the simplest expressions. So for the other one, we have the truncated hexagonal tiling, truncated square. As we can see, they are in absolutely continuous spectrum if their S prime is in this given interval. So as we can see in square, hexagon, and truncated square tiling, they coincide with the spectrum of the one-dimensional Schrodinger operator. But the rest, they have just subset of this, the spectrum of the Schrodinger operator in one dimension. And we have the other one. So as we can see, we have here, we summarize the matrix that we come up with the characteristic functions. We have 36, 30, and 24 here, 24 by 24. I think I will skip here. This is just some method how we get the interval for our absolutely continuous spectrum. Actually, I use some graphs, but I think I will skip here. So now the for the non-even potential. So if we assume that the potential is non-even, but I think we only have 3 tilings here. So it means that for triangular, we have here the Hill discriminant is an element of this interval. And of course, this is well known in the one-dimensional Schrodinger operator. But this one, for square and hexagonal tiling, we have S prime C is in this interval 0, 1. So we are not familiar with this one, but we will characterize this later. And if we assume this on the line, this is on the line, we assume this eigenvalues on the line segment. It means that Dirichlet, at a given point, we have the function value are all zeros. And then Neumann means the derivative. This is the conditions for the derivative. They are 0. So we have Dirichlet, Neumann, Neumann, Dirichlet. And we have this following inequalities, the relationship of these eigenvalues. So we have this. And we actually characterize this, that if Q is in this space, then for the periodic quantum graph associated with the hexagonal and square tiling, the absolutely continuous spectrum is actually given by this. Okay, so we will just, this is we have the Neumann-Neumann, the first Neumann-Neumann eigenvalue to infinity. Just exclude all intervals between this Dirichlet and Neumann-Neumann, and then interval between this Dirichlet-Neumann and Neumann-Dirichlet. So we have this one. I think we still have time. So now I defined this Dirac point that I've mentioned a while ago. So the idea of these definitions, we get this from Du and Cookman, that this point is a Dirac point of a periodic quantum graph if this lambda is an eigenvalue with algebraic multiplicity 2. And we have here, around this point, we satisfy this conical singularity. So we have a conical equation around this given point, given by this. Okay. So we recall in line. So we have mentioned a while ago that we have this. And the Hill discriminant, this is should be lambda. And this is the Hill discriminant, and the spectrum of the line will be between, if this delta is between -2 and 2. And this can coincide. For example, here, lambda 3 and lambda 4, they coincide. And if they coincide, the spectral bond meet at this. And for that, if they meet, so we have some candidate for the Dirac point. So actually, for the Dirac point on one-dimensional Schrodinger operator, Pfefferman and his colleagues showed that for this given expressions, VE is should be 1/2% periodic, then H has infinitely many Dirac points except for a countable set of this epsilon. So we get this idea to have some, I think I will, so the idea here is that we get these Dirac points, many Dirac points for these quantum graphs. Okay, so at this given, so if our potential is of this form, or it means even an A half periodic, then we have a Dirac point near this number, the lambda, and our theta is at 0, 0. Okay. But if we have here, if our Q is of this form, given this I, so I will not elaborate more because I think we don't have time anymore. So then we have infinitely many Dirac points for all periodic quantum graphs associated with Archimedean tilings. Yeah. And we use these key theorems, actually, a classical theorem from Horstach to use that one. I think skip this. And we also have some Dirac points for all even potential. Yeah. I think sobra na yung oras. Ito na lang. Just summarize, all dispersion relations of Archimedean tilings are of this form. So they are polynomials in S prime. And all spectra are of band and gap structure. From explicit dispersion relations, we can understand our Q point and absolutely continuous spectrum. We show existence of infinitely many Dirac points when our Q is half aperiodic and our Q is of this form, using the Horstach results on the line. And we also show existence of Dirac points similar to the one showed for the case of hexagonal tiling that persists for any even potential. Then we can say that quantum graph model is simple enough to study, yet preserves some essential ingredients of the dispersion relations. The above may also work for some graphene allotropes. So we have here, we have many graphene allotropes that we can use this method. Okay. So I think doon na muna, sir. I will end the talk here.
Okay, thank you, Edu. Thank you. Siguro, one of the traditions after the talk, kailangan mo mag-open ng video mo.
Tradition yun, sir?
Oo.
Okay. Paano ba?
Open your video. I'm also going to turn on my video. Ikaw din, Jason, if you want to.
Yeah. Is it okay?
Yan. Okay.
Sorry, sir. Nirmirush ko na. Isang oras
Okay.
na.
Okay. Hindi, okay lang. Okay.
Yeah.
Very, 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 very nice. Okay.
Yeah.
Jason, you have question? May question ako mamaya, pero baka may question ka, Jason. Tsaka yung mga sa YouTube, baka may mga nanonood po tayo from YouTube. Si Ma'am Edith is also watching from YouTube. You have question, Jason? Nakamute ka pa ata.
Siguro one question is, aside from yung graphene structure, saan pa pwedeng makita yung application nito yung study mo about tilings?
Actually, quantum graphs has many applications. And actually, yung ano lang namin kasi, we started with just mathematics for quantum graph itself. And then we come up with, kasi yung prof ko, he started with tree and some tree and star graphs. And then he has some results for quantum graphs or actually Schrodinger operator on tree. And then he come up with he stumbled upon this paper by Cookman and Post about this graphene that approximates some energies of or band structure of graphene. And so we started this book, the introduction to quantum graphs. Actually, marami siyang applications, but I'm not familiar with other applications. There's some scattering theory And mostly they are in the mathematical physics yung applications. Yeah, and but I'm not familiar with the other applications. For example, we have the quantum chaos, and so on. It's mostly a mathematical physics. Yes. Nasagot
Okay
ko ba
lang.
yung tanong mo? Nasagot ko ba?
Okay, thank you, Jason. Yeah, may tanong si Ma'am Edits. Ang tanong ni Ma'am Edits is, actually siguro parang ano na rin to, tanong na rin ni Sir Ariel, no? Yung tanong ni Sir Ariel kasi if there are already some studies na 3D naman. Pero yung tanong naman ni Ma'am Edits, idugtong ko na din, what are the possible problems pa that will pwedeng, let's say, work further from this study?
Sa 3D, sir, meron yung mga one body, meron na rin, sir. So applicable din naman siya sa yung method. And yung iba naman, yung operator kasi na ginamit is differential operator. Yung iba gumagamit sila ng Laplacian operator. So discrete naman yung approach nung iba. So yung akin lang, yung sa amin naman differential operator. And then dun naman sa tanong na ano pa, actually sa quantum graphs marami, sir, depende sa field na gusto mo. So for example, dito meron pang hindi nagagawa pero tinatamad lang akong gawin. Yung yung nanotube naman, sir, titignan yung nanotube. So actually sa graphene nagawa na yon dun sa nila Cookman and Post na hexagon ang cylinder. So titingnan ano yung mangyayari. And then another one is the inverse problems. Inverse problems. So for example, given the spectrum, can we construct the potential? And then another thing is so yung iba naman, sir, yung finite case ng quantum graph. So ganun naman ginagawa from the spectrum. Ano yung magiging structure? Ano yung magiging kasi yung continuity, yung conditions natin, boundary and vertex conditions na consider natin is standard. We have a more general vertex conditions. So from the spectrum, can we get the structure of the graph? What are the potential of the graph? Potential ng operator acting on the graph. So marami pa naman siyang sir.
Okay, maraming mga open problems. Okay. May tanong pa ulit si Ma'am Edits, no? Pero yung itong tanong ko naman, definitely we know this is physics, no? And we are talking about graphene, atoms. Ito lang naman ay in case there will be like some physical applications. Pwede ba itong magamit to compare like materials sa kanilang conductivity ng electricity or or pwede gumawa pa ng bagong material with this? I don't know. I mean, this is just coming out of my mind. I mean, in terms of yung let's say if you're going to create microchips na mas efficient or medyo malayo pa sa level na yon. I don't know.
With respect to applications naman kasi, sir. Medyo honestly nung ginagawa kasi namin to, we focus sa math pa lang. And then lately lang na physics. So dapat kung alam ko na pala ito yung gagawin ko, first year pa lang nag-enroll na ako ng mga physics courses. So lately lang na so wala pa akong ganong idea about sa iba. Kaya nga like the quantum mechanics and so on. And then I think dun sa conductivity naman, sir, kasi if you know the band and gap structures, makakapag-conclude ka na regarding those properties. Pero yung sa atin kasi nino-normalize na namin, so yung sa approach is unitless. Pero hindi ko alam kung paano nila tinitingnan yon ng physics side. And this is actually they have a more complicated approach in getting the in computing the band the energies. For example, the band structure. They have the density functional theory. Kasi which is I think mas precise yon but very complicated. Pero ito naman kasi parang nagbibigay siya ng options na mas simple na model na parang.
Okay, so coming from that question, Alam natin there are also people sa institute natin, no, and also
Apa.
from other university na working on density functional theory like sila Dr. Darin Tutungan. So ang
Apa.
itong question ni Ma'am Edith is, ano yung mga possible collaboration na pwedeng mabuo coming from this, and kung pwede daw ba ding pang undergrad or MS level, may mga ganung level ba na problems o baka advanced? Yun.
Of course, masters pwede na siguro 'yun. Pero undergrad parang mahaba kasi kailangan mo ng ano dito functional analysis. So we have the operator theory, and ako ang kulang sa akin talaga physics side na para mas maganda yung ano. Kasi late lang na ano. Yeah. So kung mag-start siya, yung bata kung mag-aaral nito may mas maganda, may ano na siya, may idea na siya about sa quantum mechanics and also with condensed matter theory. Para may input lang siya na ano.
Yep. So, yeah, I think isa sa mga prerequisite talaga yung physics knowledge, no? May tanong si Ma'am Edith dito. Let's say sa mathematics side naman, medyo halo-halo din kasi yung ano mo, di ba? Yung area, may algebra, na may analysis, na mayroong graph theory. Halo-halo. Ano yung mga, let's say, if someone would like to go sa gantong area, ano yung prerequisites na dapat meron siya para maging successful or mag-start dito sa area na ginagalawan mo?
I think para maging successful talaga, sir, is of course kasi kapag math alone you can pwede ka namang mag-ano pa rin pursue math if math alone lang yung focus mo is of course functional analysis, and depende naman siya sa mga topics, and differential of course differential depende sa approach mo. Kunyari ang approach mo ay yung differential operator, so mas maganda may idea ka ng ODE and PDE and some differential operators. And pag ang approach naman gaya ng iba, ang sa kanila naman ay Laplacian operators, discrete. So dapat magaling ka sa matrices, linear algebra, and so on. And then of course, para mas maka-move forward ka, mas maganda na may alam ka rin sa physics, sa quantum mechanics, and so on. And yeah, condensed matter theory, and so yun yung mga kailangan. So in terms of background, kailangan talaga ng ano, functional analysis. Pero yung functional analysis, focus, kasi maraming ibang books na functional analysis. So may functional analysis focus on operator theory, different books. For example, Conway, focus lang siya sa mga operator theories. And for example, Lux, and then meron namang sa physics, Reed and Simon. Meron silang book na Reed and Simon. Ito yung mga theoretical physicists na mas maganda siya. Focus naman dun. So yung functional analysis na towards differential PD and ODE yung approach. Pwede. Yan. Pero pag yung functional analysis mo ay yung sa operator theory, medyo iba yung iba yung focus.
Okay. Sige. Thank you, Edu. May iba pa bang question? Jason, may question ka pa sa YouTube? Wala na naman. Ma'am Edith, do you still have questions? Pero ano daw, nice daw yung talk, sabi ni Ma'am Edith. Okay.
Ha?
Okay.
Nantok nga ako eh.
Naka-nosebleed ba? De joke lang. Jason, okay na tayo, no? Sige, so we're not going to make this webinar very long para yung mga manonood ulit nito sa YouTube, mapanood ulit nila. So ano po to, permanent na naka-upload sa YouTube. So please subscribe and like yung ating 1UP Applied Mathematics YouTube channel. So without hindi na patatagalin kasi magluluto na si Edu ng kanyang lunch. Okay. So thank you very much, Edu. Thank you.
Thank you, sir.
Thank you
Thank
very
you so
much.
Yeah.
Thank you, Jason. Thank you for those people na nasa YouTube at nasa Facebook. So again, this is the 1UP Applied Mathematics webinar series, and we are hoping na sa susunod na mga na mga talks ay nandyan pa rin kayo. And I hope also na sa mga susunod na talk ay mas marami pa tayong maakit na speakers from different campuses ng UP. And with this, thank you very much. Happy lunch. Stay safe, stay healthy. Thank you very much, Edu. Bye-bye.